Welcome to episode 14 of Ask the Grounding Experts, where our experts from ENS Grounding Solutions answer your engineering questions about the world of grounding and earthing. Today, our man of mystery, David Stockin, unravels the mystical secrets behind the curse of the resistance to ground specifications. Cast your spell now, David.
All right, welcome guys. Today we're going to talk about resistance to ground specifications and why for us folks in the grounding and earthing game we consider it a curse. If we had a nickel for every time we got asked about a resistance to ground spec, right? Blah, blah, blah. Why do we call it a curse? So the resistance to ground is one of the most commonly quoted specifications in all of electrical engineering related to grounding and earthing. And one of the reasons is it's easy to understand, right? So for the average electrical engineer, they think, okay, well, there's a requirement in our National Electrical Code for 25 ohms or less on our grounding rods at our homes for a single ground rod installation. And they think, okay, well, if 25 ohms resistance to ground is good, well, 10 ohms is better, and 5 ohms must be even better than that, right? And so they start putting in these specs, and they say, well, I want a good grounding system, so they just kind of randomly pick a number out of the sky and say, I want 5 ohms, for example, with not really understanding why they even may need a low resistance to ground. And so one of the couple things that are important to think about is, what is the resistance to ground of the grounding system for the International Space Station? Right? It's not like as if there's a ground wire hanging down as it flies by, tying it to ground, yet it's full of grounding. What is the resistance to ground of a 747 airplane? And it's full of grounding. Or a helicopter. Or your car is sitting on rubber wheels. Right? And in some cases, you can even think of a ship out at sea in certain cases as well. All of these things have massive grounding systems in it, and yet they don't have an electrode at all. And in fact, until 2018, the British standard and most of the international electrical code around the world, about 3/4 of the planet, did not have a requirement for ground rods or earthing rods at their homes until 2018. Right? And the reason for that is we don't need a ground rod to clear our electrical faults in most cases. We put those ground rods in there for other reasons, for objectionable currents, harmonics, transients, to make sure our surge protection devices work. There's lots of other reasons for them, but we typically don't need them to clear our electrical faults. Our electrical faults are staying on top of, right through our above grade grounding system the entire time, and doesn't utilize our below grade grounding system. And in fact, in America and under the National Electrical Code and in all the other countries associated with it, you're at the residential level, you are not allowed to use the earth as part of your fault current impedance path. Unlike under the international code, where under a TT system you are, right? You can measure the Z sub S, and if it's under 200 ohms, you're allowed to use the earth as part of the fault current path. But in the National Electrical Code, we're not allowed to use it at all. So it's very important to understand why you need a ground system. The National Electrical Code requires that if you have a single ground rod and you measure it and it's under 25 ohms, you're good. You can stop. If you don't want to measure it or it's too high, you put a second ground rod at least 6 feet apart, twice the length of the electrode ideally, right? So 20 feet apart for a 10-foot rod, right? If you have two 10-foot rods, you don't want the spheres of influence to overlap. So you get a better bang for your buck if you can place that electrode twice the distance of the electrode apart. And then you don't have to measure at all. There is no resistance to ground requirement. Now, in the telecommunication industry, the cell phone industry in particular, has requirements for 25 ohm or 10 ohm to ground, resistance to ground requirements for their shelters that they're putting the cell phone sites in. And this drives a lot of the industrial requirement for low resistance to grounds. But that said, we could float a cell site up and put it on the International Space Station and it'll work just fine. Does not need that low impedance fault, that connection to the Earth is not its the primary factor for a safe, effective system. They want a grounding system in that case to bond everything up so that there aren't differences in potential that could cause electromagnetic interference in the antennas themselves. This is something we can talk about later, why we have so many bonding requirements in telecommunications for another video down the road if you guys like. Leave a note down below and tell us if that's something you want to hear about. We can talk about it. But in this case, the resistance to ground spec isn't needed in most cases. In fact, in Motorola's R56, they tell us right in the standard that the shape of the grounding system is far more important than the overall resistance to ground. So now, this isn't to say that resistance to ground has no place for us. There are pieces of equipment that need it. Some of our antennas, like the shortwave antennas, back after World War II, right? The soldiers came back from the war and they wanted to talk to their buddies that were on the other side of the world in some cases, or on the other side of the country, and telephone calls were so expensive they turned to shortwave. And now the shortwave uses what's called the half wavelength theory of antennas, or a quarter wavelength or eighth wavelength, and it requires a good grounding system. The lower the resistance to ground, the more efficient that radio signal would be broadcasted. Right? So some antennas do need a good grounding system, satellite systems. An MRI machine at a hospital, the magnetic fields need to be dumped into the grounding system, and if there's too high of a resistance to ground, it'll get a bounce back and it'll impact the image, which is really bad, right? So we want to have a nice low resistance to ground for MRI machines, satellite systems, certain antennas. There are pieces of equipment that do need a nice low resistance to ground, and if you're an engineer and you're designing a ground grid for that, good thing to know. But if you're simply got a site and you just are randomly putting down a spec, you should understand the consequences of this. What are the consequences of a low resistance to ground requirement? The closer to zero you want to go, the more exponential the cost is going to be. Right? Nothing is going to be zero. Right? Even a superconductor isn't zero resistance. Even if the planet was made out of solid copper, it wouldn't be a resistance of zero, right? So the closer you make that spec, the more and more, the larger and larger our grounding system has to be in order to achieve that resistance to ground. If you measure the soil, right, a given soil will only allow a 10-foot ground rod to measure to a certain resistance. It's not like you can go down to Home Depot and say, give me 2 25 ohm ground rods and a 15 and throw in one of those 5 ohmers while you're at it. No, it doesn't work that way, right? If you've got a 100 ohm meter soil, a 10-foot rod is going to equal whatever the math is. That's it. It won't be higher and it won't be lower. It's impossible for it to be anything other than what the laws of physics allow it to be. So when you put in a resistance to ground spec, and you have a land area that's 10 foot by 10 foot, for example, right? If you're putting a spec, say 5 ohms, and you're sitting on solid rock, well, good luck, right? That's a bad spec, and whoever put it on there, I'm sorry to say, you did a bad job with your spec. There's no way you're going to achieve 5 ohms resistance to ground out of a single ground rod sitting on top of a mountainside. It's just not going to happen. You might be lucky if you get 1,000 ohms, right? And again, obviously, it's not always even important, right? The resistance to ground, when resistance to ground goes higher, our difference in potential, what we call the ground potential difference, needs to be lower. It just changes the requirement from one side. If our resistance to ground is high, we want to make sure our ground potential difference gets lower. What do we mean by that? Take that 747 up in the air. Let's say we measured it from wingtip to wingtip, stem to stern, and let's say it measured 1 ohm across it. That's the resistance of that airplane across any given point was 1 ohm. And say it's flying in there and it gets hit by lightning. And in fact, studies show that every commercial airliner will be struck by lightning about approximately 1 time per year across the globe. It means every commercial airline does get hit by lightning at some point, and oftentimes the pilots don't even know it was struck. But now if that airplane is 1 ohm and it gets hit by 100,000 amps worth of lightning, well, that's Ohm's law, right? 100,000 volts is going to form across that airplane, and that's too much for the electronics to handle. But if we made sure we stretched some copper wires and we lowered the overall difference in potential across that airplane, so we put some extra copper wires in it and we made sure everything was bonded properly and had a nice low impedance fault current paths everywhere, and we lowered it so wherever we measured it, if we measured the resistance to that plane now from tip to tip and stem to stern, and we got 0.001 ohms, right? Now all of a sudden we would lower when that 100,000 amp strike hits, now we only get 100 or 1,000 volts across our plane, and that's something our surge protectors can protect us against, and that's levels that our equipment can manage. And this is why these airplanes will fly through the air and get hit by lightning and the pilots don't even realize it. When we're designing our grounding systems, we rarely can control the voltage we're going to see. We can rarely control the current we're going to see, but we can control the resistance or the difference in resistance from any two given points. So when you're designing a grounding system, if you've got to think about being able to lift that system into space, and it should still function properly in most cases. And that exception could be certain fault clearing conditions if you're dealing with utility level antenna systems, certain electronic systems such as MRI machines, etc. But for most cases, for 90-something% of all the applications you're ever going to run into, resistance to ground really isn't the most important factor, and it should not be your primary driving force in designing a resistance to ground spec. Hence why we call it the curse of the resistance to ground spec, because it's generally a curse. Some engineer somewhere put 5 ohms randomly into a spec, and now everybody's chasing their tail trying to design a grounding system in soil that could never possibly achieve 5 ohms. You're far better off, if you want to put a good spec into the ground, say, I want my grounding system from any given point to have a continuity of less than 0.1 ohms. That's a good spec. Or I want a ground potential difference during a fault of less than 1 volt across my grid. Right? That means I'm going to have a safe system like a bird on the wire. We don't care if the substation is 100,000 volts during a fault. Right? Who cares? As long as everything's 100,000 volts. That means the difference in potential is 0 and everything is safe. Right? Like the bird on the wire, right? You can get on the high voltage wire too. Of course, we certainly don't recommend it. But as long as you don't touch anything else, as long as your entire body is charged that voltage, you're fine. It's the second you touch something else and that difference in voltage happens, that's what kills you. Right? And so again, it's not the resistance to ground that's important. It's often far more important to have the ground potential difference, or the difference in voltage that can occur across that grid is far more important for a specification than the resistance to ground. It's a very complicated topic. You obviously need to design your grounding systems and place the specs for those grounding systems in accordance to the systems you're designing that grid for, right? But before you go slapping down resistance to ground specifications, please figure out whether or not you really need a low resistance to ground, because a grounding system that works in clay and one that works in solid rock could be the exact same system, and they could effectively and efficiently work very well and have very different resistance to grounds. One could be very low and one could be very high. And they can both be super efficient, super effective grounding systems, because again, the resistance to ground isn't the primary driving factor for most grounding systems. And that's our video today on the curse of the resistance to ground spec. I hope you find it useful. Mash that button down below and click a thumbs up, and write a comment and let us know if you want some more information like this. We'll certainly do some more videos in the future. Thanks a lot.
Thanks so much for watching. If you found this episode helpful, please give us a quick like down below and subscribe to stay up to date on future educational videos we will be publishing. And feel free to post questions or comments below as well. We might even feature your questions in future videos. If you'd like to learn more about the amazing world of electrical engineering and grounding, be sure to check out our certified online courses at the links in the description below to kickstart your career. See you next time.